Hi, welcome back. This is homework 5, part C, and here I will be drawing the block diagram for a cascade controller in which there is an inner loop process transfer function in which we have a valve in our system. So to begin with our cascade block diagram, so we can start with our initial height set point, HSP, and that is going to enter in at our comparator. So we will have a plus minus, and then next from here we will be entering into our first outer master controller, so we can call this GC, and we can denote that this is our outer, so we have that here. So next from here we will then go into another comparator where we will be taking the plus minus. And this outer control is basically the master controller in which we will be finding out what our actual height set point will be, and depending will give us the flow rate that we are looking for. So from here, moving into our inner control, so we can denote that as our GC, and we can call this our inner. And from our inside loop, we know that we are going to have a process transfer function for our valve here. So from our inner control, we will be entering into our GV transfer function, and this is for our valve. From our valve, that is what is going to be outputting our flow rate in order to reach our desired set point. So from there, we will enter into our GP, which is our final process transfer function, and then from there we are given our height. So for this inner feedback loop, we need to create an inner loop in which we are going to just worry about our inner and our valve. So this feedback loop will come back to there, and then it will cycle through depending on what the flow rate is going to yield. So that is for our inner loop. And then lastly, we will come from our original comparator, and then we will return all the way across our feedback control loop, and we will come back slightly to the right of our process transfer function. So this is our cascade control loop, and we also need to note that we can also have a measurement device, and we can call that GM. And that can be on both our inner and our outer loops. So this is our cascade control loop for the inner and outer feedback control loop, in which we are using a valve to control our desired flow rate.
Hi, welcome back. This is going to be homework 5, part C 1 and 2. So we had just finished drawing the block diagram for the cascade controller. We are now going to want to import this into our code, and we are going to want to use our process transfer function for our valve GV, and that's going to be equal to 1 over 0.1s plus 1, in which the inner loop proportional controller gain is equal to 1.2. And then for our master loop first order plus time delay transfer function is going to be equal to 0.12 times e to the negative 5s, and that will be over 12s plus 1. And our outer proportional integral controller with controller gain kc, and we'll have a reset time of tau I is equal to 0.5. We will then be trying to find the optimal controller gain to yield approximately 30 degrees of phase margin stability, and then we will want to simulate this closed loop response from above to a unit step change and set point. So to begin, we can go ahead and head back into our code, and we can start with this cell, saying that we are in part C now. Go ahead and change the title of this to include part C. All right, so to begin, we know that our our inner loop proportional controller gain is going to equal to 1.2. So we can go ahead and call our GCI is going to be equal to 1.2. And then next we can go ahead and type in our process transfer function for our valve, and we can denote that GV. And as I stated earlier, our GV is going to be equal to 1 over 0.1 times S, 0.1 times S, and then that's going to be plus 1. All right. So next, we want to go ahead and define what our G of our inner loop is going to equal to, and we can use our shortcut for this and go ahead and say that our inner is going to be equal to our inner GC controller, so GCI. That'll be multiplied by our process transfer function for the valve, and then this is all going to be divided by 1 plus GCI times GV. So next we can go ahead and code in our GC for our outer, and this is going to be equal to our KC value of 1 times 1 plus 1, and then this is going to be over we have a reset time equal to 0.5, be divided by our reset time of 0.5 times S, and our 1 here is what is going to be our variable that we are changing. So I'm going to go ahead and hard code this in, saying that it's going to be our KC for part C, in which we are using the cascade controller. So I'm going to change this to KC for C, and then I'm just going to change this and make it 1. That way we can change our variable here instead of in the transfer function. So I'm going to type, this is our variable to change. Okay, so next we need to define what our outer GP is, and that is going to be our process transfer function, and this is going to be equal to 0.12 times the exponent of negative 5s. So we can type in 0.12 times the exponent of negative 5 times s, and this is all going to be over 12s plus 1. Oops. Okay, so now that we have that in, we now want to define what our GC for our closed loop is going to be, underscore C, denoting our cascade control, and this is going to be equal to our outer control loop, or our outer controller, multiplied by our outer process transfer, and then this will also be multiplying by our inner control loop, so we can just multiply by GI, and then this will all be divided by 1 plus our GCO times GPO times GI. Shift enter. Okay, so our next step here in this puzzle is going to be, or our next piece in this puzzle is going to be creating our Bode plot. So as we did before, we need to define a G, and this G is going to be equal to our GCO times GPO times GI. And this is the numerator in our cascade closed loop control. So next, what we can do is go ahead and grab some code from our previous part, and we want to grab this, and we can hit Control C, come back down here, Control V, paste that in. However, here for our omegas on our x-axis, we want to change this -2 to a -3, and then we're going to increase the number of indexes that it will be able to hold and raise that to 500. And then our GJ omega is going to remain the same, in which we are substituting our S to be omega times J, in which our J is the square root of -1. And then we are going to be plugging in our W's. And then for our imaginary and real, we are transforming them into our np.imaginary and our np.real numbers. And then again, our magnitude ratio m is going to be equal to the square root of I squared plus R squared. And then for our phase angle, we are going to be using np.unwrap and then arctangent of I and R. And again, we need to multiply this by 180 over pi in order to transform or translate this into degrees instead of radians. So now that we have this, we now want to go ahead and grab our previous plotting cell. So we can go ahead and select this. Don't know why that was still selected. Control C. Come all the way down here. Control V, paste this in. Okay, so now that we have that pasted in here, we now want to reference back to our homework. And what we're looking for is the controller gain to yield approximately 30 degrees of phase margin stability. So what that means is instead of our previous parts when we were looking at the crossover frequency of 180 degrees, we now want to have a fudge factor of 30. So instead of having our y-axis in increments of 180, we now want to go ahead and subtract 30, and that will make us have a increments of 150. So shift enter. So here is our Bode plot, and we have our axes of 150 for our phase angle. So if we drag this over here to approximately 150, we are around 0.73, maybe 0.725. So then we come over here to our 0.0725. So it's right around here. And we have a magnitude of 1.37. So we know that that is above 1 and we are slightly too high. So our next step is going to be to change what our KC value is for our outer loop. And since we are too high, we need to go ahead and lower this. So we can cut it in half to 0.5 and then shift enter through. And again, we are at 150 around 0.0725. So we go 0.0725. We are around 0.66. So jumping from 1 to 0.5 was too significant. So we can go back up here and we can try to go in between, and we'll try 0.75. Okay, so we look for 0.0725. Or what was it? 150. 0.073. So our 0.073 is yielding 1.02. So it looks like we're slightly too high. So let's try cutting this down a little bit. And then we look for our 0.073. And we are right at. So that is going to be our controller gain to yield approximately 30 degrees of the phase margin stability, in which our KC is at 0.0725. So next for this assignment, I will be simulating the closed loop response to a unit step change in set point. So I've already defined what our GCL, our closed loop for the cascade controller, is right here. So what we need to do is go ahead and snag this piece of code. We can hit Control C, come back down here, Control V, paste that in. And what we need to update here is our closed loop function. So we're going to make this _C, which we had denoted above. And then for our name, we can go ahead and change this as follows. And then we can hit Shift Enter. So as you can see, at our phase margin of 30 degrees and our optimal controller gain for that scenario, we are yielding a stable response. All right, that is it for homework 5 part C. Thank you for watching.